Welcome to our journey into abstract algebra. Today, we are going to explore a fascinating concept known as the generators of cyclic groups. Imagine having a single building block that, when used over and over again, can construct an entire complex structure all by itself. We will uncover how these special elements work, how to find them, and why they are the absolute foundation of the digital security that protects our modern world. Let us dive in. To begin, let us think about a board game on a circular track with 12 spaces, much like a clock face. If you have a card that moves you forward exactly 5 spaces and you keep using it, you will eventually land on every single space before returning to the start. In abstract algebra, a group is a set of elements combined with an operation, like addition or multiplication. A cyclic group is a special type of group that can be completely generated by just one single element repeating itself. We call this specific element a generator. Understanding why this matters is crucial because it shows us that incredibly complex mathematical sets can be perfectly described by just one simple action. Now that we understand what a cyclic group is, let us look at how we write it mathematically. Conceptually, this formula simply lists out every single state you can reach by repeatedly applying the generator. We use the letter G for the group and we put the generator A inside angle brackets to show that it builds the whole group. The symbol E represents the identity element, which is what you get when you apply the operation 0 times. The letter N represents the order, which is just the total number of elements in the group. If the group size N increases, the cycle just gets longer before it wraps around back to the identity element. This mathematical notation leads us to an important question. How do we know which elements will be generators? It turns out that some groups have only one generator, while others have many different elements that can each build the whole group on their own. Instead of guessing and checking every single element, mathematics gives us a powerful shortcut. We can determine if any element is a generator by looking at its relationship with the total size of the group. Specifically, we look at the greatest common divisor, or GCD. When the GCD of two numbers is exactly 1, they share no common factors, and we call them relatively prime. This simple property is the key to unlocking all generators. Building on that idea of the greatest common divisor, let us look at the formal theorem. Conceptually, this formula tells us exactly when a new element will successfully generate the entire group without getting stuck in a smaller subcycle. The symbol a to the power of k represents our candidate element. The double arrow symbol means if and only if, showing that this rule works in both directions. The function GCD checks the greatest common divisor between the power k and the group size n. If you increase k to a number that shares a factor with n, the GCD becomes greater than 1 and the element will fail to generate the group. It must be exactly 1. Before we move on to proving this theorem, let us see it in action with a concrete example. We are given the group of integers modulo 8 under addition and we are asked to find all of its generators. Because the group contains the numbers 0 through 7, its total size or order is 8. In additive groups like this, the number 1 is always a basic generator. To find the others, we apply our theorem. We need to find every integer k in the group such that the greatest common divisor of k and 8 is exactly 1. This means we are looking for numbers that share no common prime factors with 8. Continuing with our modulo 8 group, let us find those specific numbers. Since 8 is simply 2 to the third power, its only prime factor is 2. Therefore, any even number will share a factor of 2 with 8, meaning they cannot be generators. We are left with the odd numbers 1, 3, 5 and 7. To be absolutely sure, we can test the number 3. If we repeatedly add 3 to itself modulo 8, we get 3, 6, 1, 4, 7, 2, 5 and back to 0. We hit every single number. Physically, this means taking steps of 3 around an 8-space circular board will visit every space. Our final answer is that the generators are 1, 3, 5 and 7. Now that we have solved an additive group, let us tackle a multiplicative one. We are asked to find the generators for the group U10, which consists of all positive integers less than 10 that are relatively prime to 10. First, we must identify the elements. Since 10 is 2 times 5, we exclude all even numbers and all multiples of 5. This leaves us with the set containing 1, 3, 7 and 9. Because there are 4 elements, the order of our group is 4. In this multiplicative group, the identity element is 1 because multiplying any number by 1 changes nothing. We will use this setup to test for generators. Moving forward with our group of size 4, we need to see if it is actually cyclic. We do this by picking an element, like 3, and computing its powers modulo 10. The first power is just 3. The second power is 3 squared, which is 9. For the third power, 3 cubed is 27, and when we divide by 10, the remainder is 7. Finally, 3 to the fourth power is 81, which leaves a remainder of 1. We have reached the identity element exactly on the fourth step. This proves that the powers of 3 successfully generate all 4 elements of the group without repeating early. Having verified that 3 is a generator, we can now easily find any others. Because the group is cyclic and has an order of 4, we can apply our generator theorem. We look for powers k such that the greatest common divisor of k and 4 is 1. The only positive integers less than 4 that fit this rule are 1 and 3. Therefore, the generators of our group will be 3 to the first power and 3 to the third power. We already calculated that 3 cubed is 7 modulo 10. Physically, this means both 3 and 7 can independently generate the entire multiplicative structure. Our final answer is that the generators are 3 and 7. Now that we have successfully used the theorem in multiple examples, let us understand exactly why it works by proving it. We will focus on the forward direction. Assuming that the element a to the power k generates the entire group, we will prove that the greatest common divisor of k and the group size n must be exactly 1. The mathematical reasoning starts with the definition of a generator. If a to the power k truly builds the whole group, it must eventually build the original building block, a. This means there has to be some integer power m that we can raise it to get a to the first power. Multiplying the exponents gives us a direct relationship to work with. Following our exponent relationship, we must account for the fact that the group is cyclic. Because the group repeats itself every n elements, the exponents k times m and 1 do not have to be exactly equal numbers. They just have to land on the same spot in the cycle. We write this using modular arithmetic, stating that km is congruent to 1 modulo n. To make this easier to solve, we convert it into a standard algebraic equation. This means the difference between km and 1 is exactly some multiple of n, which we write as q times n. By simply moving the terms around, we get a linear combination. K times m minus q times n equals 1. This sets us up perfectly for the final conclusion. This brings us to the final step of our derivation. We have arrived at an equation where a linear combination of our power k and our group size n is exactly equal to 1. In number theory, there is a fundamental rule called Bezout's identity. It states that if you can combine two integers in this linear way to equal 1, those two integers can share no common factors other than 1. Therefore, their greatest common divisor must be exactly 1. The intuition here is beautiful. If the step size shared a factor with the track size, you would get trapped in a smaller loop. Because it equals 1, you are guaranteed to visit every single element. This completes our proof. To truly cement the proof we just completed, let us look at this visual representation of a group of size 6. On the left, you see what happens when our step size is 1. The green arrows jump from 0 to 1 to 2 and so on, hitting every single node on the clock face before returning to the start. Because 1 and 6 share no common factors, it is a perfect generator. On the right, we take steps of 2. The red arrows jump from 0 to 2 to 4 and immediately back to 0. We get completely trapped in a subcycle of even numbers, missing the odd numbers entirely. Because 2 and 6 share a common factor, 2 fails to generate the whole group. Now that we have seen the mechanics visually, you might wonder why generators of cyclic groups matter outside of a math classroom. The reality is that they are the absolute foundation of modern digital security. When you send a secure message online or log into your bank, your computer often uses an encryption method called the Diffie-Hellman key exchange. This algorithm relies entirely on the properties we just learned. A computer picks a massive prime number to create a giant cyclic group and then selects a specific generator to mix the secret keys. Because it is mathematically easy to repeatedly apply the generator to compute powers, but incredibly difficult for a hacker to reverse the process, your data stays safe. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that a cyclic group is a mathematical structure that can be completely generated by repeating just one single element. Second, we discovered the powerful rule that an element will act as a generator if and only if its power shares no common factors with the total size of the group. We proved this using Bezout's identity and saw it work in both additive and multiplicative examples. Finally, we saw how this simple but profound concept protects our modern world through cryptography. You now have a solid understanding of the generators of cyclic groups. Excellent work!